Okay, now let's get started. Today we're going to talk about loss imaging for general reflectance. We know that loss imaging is about reconstructing objects that are around the corner or blocked by some diffusers. In last lecture, we've discussed some approaches to solve this challenging problem, include filtered back projection and light cone transfer. However, these approaches are either slow, assume a hidden object with Lambert reflectance, or limited to the planar surfaces and confocal environments. Today, we're gonna introduce two new approaches to overcome these limitations. The first one is a frequency domain method called FK migration. F refers to the temporal frequency, can be thought of as the number of waves per unit time. Well, K refers to the wave number, which means the number of waves per unit distance, and it is often called spatial frequency. This method is inspired by the inverse method used in seismology. Seismology means 地震学. In seismology, FK migration is used to map out the structure of the underground surfaces. Shock waves generated by explosion scatter off the underground structure and are then recorded by the sensors at the surface. Here, the shock waves is analogous to the wavefront of light, which propagates outwards from each illuminated point on the wall. Rather than modeling the two-way propagation of light from the wall to the object and back, we can think of the light. As being emitted by the hidden object at time zero, and traveling at half the speed of light to the wall. Okay. The captured environment thus contain the intensity of a wave field arriving at the wall of time. Assume that this surface is planar and located at z equals to 0 for this moment. Therefore, we can directly access certain properties of psi x y equals to 0t with the imaging system. Here, psi x y t represents the electromagnetic radiation at every point in space x, y, z, and time t. And reconstructing the geometry of the hidden volume corresponds to find out the value of the wavefront of time t. This is a boundary value problem, which requires us to migrate the field from the one boundary at the wall, z equals to 0, to another in time, t equals to 0. This kind of problem can be solved by FK migration in three simple steps. Starting with measurements at the wall, we take the Fourier transform to calculate the spectrum. Then we interpret the spectrum based on the constraints from the wave equations, and we'll discuss the wave equations later. And finally, we apply the inverse ft to get the hidden volume. Here is a reconstruction pipeline. Psi refers to our original measurement. Phi bar is the spectrum of the measurement after ft. And phi is a new spectrum after interpolation. Pretty clear, right? Now let's dive into the details. We begin with the wave equations, which describes the propagation of electromagnetic radiation, like light. It could be used to express the kinfolk in-loss imaging formation model in the following parts. Here, psi xyzt represents the electromagnetic radiation at every point in space xyz and time t. In free space, the wave equation constrains the propagation of psi in space and time according to equation 2. Where the Laplacian operator is defined over the spatial dimensions, and the speed of the light in the medium is usually defined as 3 times 10 to the 8th meters per second. Wave equations can be derived from the Maxwell's equations with some basic operations. Here, capital E and B are electric and magnetic fields, respectively. Mu is permeability, 磁导率, which means the degree of magnetization of a material in response to a magnetic field, and epsilon refers to permittivity, 介电常数, which represents the coefficient of the insulation capability, 绝缘能力. Dot product refers to divergence, 散度. Cross product refers to curve, 旋度. Let's look at the second, the third, and the fourth row. The curl of a vector field here equals to the gradient of the divergence of the vector field minus the Laplacian here, this part. In a source-free region, divergence of the field will be 0 here. So this part is 0. The gradient of the divergence of the vector field is 0. Then we set V equals to 1 over squared mu epsilon, and we could get the wave equation just like mentioned before. Now, let's focus on the reconstruction pipeline. As mentioned before, we first take Ft to the measurements per psi. This is the original measurement. And I get a spectrum phi bar, which is realized by equation 3. Notice that when V equals to 0, equation 3 becomes a three-dimensional Ft. Here, k is a wave vector, indicating the direction of the propagation of the individual plane waves. And the wave vector k and the frequency f are related by the dispersion relation, 色散关系, which shows in the middle figure. From the dispersion relation and its Jacobian, we could get equations at the red corner, quite obvious. Then we use them to perform a change of variables, shows as equation 4. It represents a weighted 1D interpolation, known as Stewart interpolation. Phi is the interpolated spectrum, and it can be used to reconstruct the original measurements in the future. Finally, we take the inverse 3D Ft to the interpolated spectrum phi, shown as equation 5. Now, we briefly deduce equation 5, and for the detailed derivation of other expressions, you can refer to the supplementary materials. We first express psi in terms of its spectrum as equation 6. Here, function psi and function phi are related by a ft operation on the spatial dimensions only. Then we substitute it into the wave equation, produces equation 7. In equation 7, the integral is 0 only if its spectrum phi is 0 for all frequencies. In other words, for the expression 7 to be true, we require equation 8 to be true. Well, however, equation 8 is a linear second-order ordinary differential equation, and its solution has a form of equation 9. The function phi positive represents a planar wave propagating in the direction positive k, and phi negative represents the wave propagating in the opposite direction, negative k. It is convention that the wave propagates in one direction for each wave vector k by setting one of phi positive or phi negative to 0. We assume phi negative to 0 here, and by plugging this solution back into equation 6, we could get the equation 5, where phi equals to phi positive. And when t equals to 0, both function psi and phi are related by ft operation. Okay, now let's show some of the confocal experiments firstly. The hardware prototype consists of a fast-gated spider laser detector, electronics, various opticals used for focusing and scanning the system, enables fast high-resolution scanning with an average laser power of roughly 10,000 times greater than previous in-loss systems. The temporal resolution of the system is about 17 picoseconds. Besides, since the wall randomly polarized light reflection, we said the polarized beam splitter blocks half the returning light. The results are shown as this. The reflectance property of these objects shown in this figure ranges from diffuse to specular. We could see that both the reconstruction of key migration LCT tends to similar for diffuse and glossy objects, though FK migration generally appears less sensitive to noise present with the environment. However, FBP tends to perform poorly when environments contain a large amount of noise. With respect to the disco ball example, FK migration provides a reasonable reconstruction of the sphere surface. However, while FBP and LCT suffer from numerous streak-like artifacts, 条纹. To evaluate the reconstruction method with respect to noise, we perform reconstructions on measurements of a bike captured over different exposure times. Here, 10 minutes and 180 minutes. The shape of the bike is discernible after 108 minutes for all three methods. However, the FBB reconstruction result is noisier, and LCT results appears to be blurred. FT migration produces high fidelity reconstructions while also being robust to noise. With the 10 minutes exposure, the relative reconstruction quality of FK migration and LCT remains the same, but the reconstruction of quality of the FBP decreases appreciably due to its sensitivity to the noise. Here is a dynamic comparison of these methods. We could see from that FK migration produces a clean, high-quality results. So far, we've discussed some confocal and loss reconstruction. At the beginning of this lecture, we noticed that FK migration could handle non-confocal measurements and a non-planar surface. But how? Now let's take a glance at how these kind of problems are settled in this paper. For non-confocal measurements, the authors introduces a pre-processing step to convert it to confocal measurements. It approximates the measurements at the confocal sample at the common midpoint location of the non-confocal source and detector. Consider the in-loss imaging scenario in which sensor images a point XCYC and a pulsed laser illuminates a point XLYL on a wall located at Z equals to 0, and the hidden volume contains a single scatter area located at XC plus XL over 2 and XYC plus YL over 2. The non-confocal time of flight t is related to the time of flight t0 of confocal measurements position at the midpoint location by this equation. Here, xc minus xl and yc minus yl represents the offset. The process to calculate the confocal approximation to non-confocal measurements consists of 3 steps. We reparameterize the measurements by their midpoint locations and offsets, and then for each midpoint offsets, we interpolate the transient measurement using following equation to estimate the confocal transient at the midpoint. And finally, we average the measurements across offset dimensions to yield the 3D volume of confocal measurements sampled on the midpoint grid. As for non-planar sampling surfaces, we consider the case of sampling measurements at a constant offset location, Z equals to delta Z. And we desire to extrapolate the value of the field at Z equals to 0. As applied to equation 3, this can be expressed as equation 10. This extrapolation procedure can be applied to migrate data sampled across a general non-planar surface onto a visible planar wall at Z equals to 0. Let the positions of the non-planar surface be parameterized by the function delta dxy. Then the procedure involves 3 steps. We first isolate the measurement transient at each spatial location xy and compute its 3D ft. After that, we apply the extrapolation operator to shift each transient by delta z xy, and finally, a convention, we linearly combine the results spectra of all shifted transients to recover phi bar. At the end of this paper, we analyze some of its pros and cons. We could see from the table that the proposed FK migration algorithm is fast, robust to non-Lambert reflectance properties, and could produce high-quality reconstructions for non-planar sampling surfaces. What's more, FBP and LCT require some parameter tuning, especially in the presence of noise, while FK migration works by simply redistributing frequency coefficients and has no tunable parameters, which will be more easier. Okay, so far so good. Now let's turn our attention to the second method in today's lecture, format passes-based in-loss imaging. Rather than focus on the radiometric aspect of the in-loss imaging problem like before, these new approaches allow us to treat in-loss reconstruction from a pure geometric perspective. First of all, what are format passes, and why could they be used to reconstruct in-loss objects? Actually, format passes are the light passes, either be specular reflections here and here, or are reflected by the object's boundaries here. They encode the shape of the hidden objects. So we could do the inverse process to recover the unlost objects. But how? How could we make this happen? In this paper, the authors proposed four steps to reconstruct the in-loss objects. Let's have a glance at its reconstruction pipeline firstly, and the details will be introduced in later slides. In the first step, we collect transient environments I at multiple points V on the visible surface V. We know that transient is a radiance from photons with time of flight t. Then, the authors proved that format passes corresponds to discontinuities in the transient environments. For each measured transient, we can detect the path lengths where the transient is discontinuous. This corresponds to sample of multi-valued format passes function tau fv. In the process of reconstruction of in-loss image object, the author proposed the so-called format flow equation. We reconstruct from each branch set of points, either on the boundary branch tau f1 v, blue one, or the interior branch tau fv2, the red one, of the in-loss shapes. Before that, we need to compute the gradient of the format path lengths function tau f by interpolation. Now let's dive into the details. We'll consider transient imaging system. The detector records the transient I equals to the irradiance from photons with time of flight t. Its formulation is a path integral formulation of light transport, which integrates all light transport passes in the scene. Here, the function f is the radiance throughput of the path, which depends on the geometry and the material of the scene, the spatial angular emission of the light sources, and the spatial angular sensitivity of the sensor. Delta function indicates that we just measure the points on unlocked surfaces whose distance is to point V is 0.5 tau. And here APQ is a corresponding area measure. Authors of this paper found that format passes corresponds to transient discontinuities. In the left figure, XFI is the points on the unlocked surface. We could see from the figure on the top left that when we scan the scene from the right to the left, the path length is tall, goes up, and then fall off. And we could get the relation between transient I and path length is tall. If we ascendingly saw the path lengths, we could see that the transient at point tau f1, 2, 3 is discontinuous. This feature could be used to detect format passes, and we define this as a format path length function tau fv. As each transient I can be discontinuous at more than one path length, tau fv is a multi-valued function. Consider a branch of the format path length function tau fv evaluated at visible surface V. Assume that there is a unique point xf with tau xf equals to tau fv. Then we have this formula. Since format path lengths double the distance from xf to the unlocked surface to the visible point V, we have 2 here. Proof details are provided in the supplementary materials. We know that format passes are either specular or at the object boundary. The format path length function type V can be set as double distance between surface point xf and the visible point V. And then we could rewrite format flow equation as the right one. It indicates that an unlocked point xf generating a format path can be uniquely reconstructed from the corresponding visible point V. The path length is tau fv, and the gradient of path length is. Notice that in the equation top right, we require knowing the gradient of tau fv, which cannot be measured directly, but we can estimate it through the interpolation. For simplicity, we discuss here only in the case when the visible surface V is planar. Given a format path length tau v at point V, we can estimate its partial derivatives with respect to x and y by locally interpreting format path lengths from transients measured at nearby points on the plane. We can then infer their derivative with respect to V by noting top equation implies that the norm of the gradient of tau V equals to 2. However, the equation in the red box fails when the uniqueness condition of the format flow equation is not satisfied. This can only happen at isolated points V on the visible surface. And the interpolation procedure needs to be performed separately for each branch of the format path length function tau v. Our reconstruction relies on interpreted estimates rather than direct measurements. Interpolation procedure produces an oriented point cloud, two images in the middle, and we can then use algorithms that take advantage of normal information to fit the surface representation to the point cloud with increased accuracy. Images on the right. Now let's recap the reconstruction pipeline. We collect the transient measurements I, and then detect path lengths where the transient is discontinuous. After that, we compute the gradient of format path length function tau f by interpolation. Finally, we use the format flow equation to reconstruct the in-loss objects. Dynamic reconstruction process shows as this. To demonstrate the theory proposed in this paper, the authors made some experiments at a picosecond scale and a femtosecond scale. Picosecond scaled experiments use a spider-based transient imaging system, just like mentioned before, a picosecond laser, a spider detector, and a photon counter. The temporal binding resolution of the TCSPC unit is 4 picoseconds, and the absolute upper bound in depth resolution is about 1.2 millimeters. We scanned a variety of everyday objects with convex and concave geometry of different BRDFs, including rough specular objects, cattle on the left, glossy objects, bow on the middle, and translucent objects, plastic jug on the right, and so on. Most of the objects has a major dimension of approximately 20 to 20 times 30 centimeters and are placed at a distance of 80 centimeters from the visible wall. In all cases, the reconstruction closely matches the object shape, demonstrating that the ability of the algorithm proposed in this paper to handle the variety of complex geometry and reflectance combinations. For femtoscale experiments, we use an optical coherent tomography system. Spatial and temporal incoherent LED illumination allows us to combine transient imaging with diagonal probing. In the context of confocal scanning, we can simultaneously collect transient at all points on the visible surface without scanning. This experimentation has depth resolution of 10 microns. We place a coin at a distance of 10 millimeters from the visible surface and collect the transient measurements on an area of about 40 millimeters by 40 millimeters at 1 million pixel grid of points. We can see that the reconstructed details is in close agreement with the ground truth measured directly in the line of sight. Now let's have a glance at its pros and cons. Format passes method treat in-loss reconstruction from a purely geometric perspective, offers new insights into the in-loss imaging problem. What's more, it could recover in-loss objects that are around the corner or hidden behind the diffuser. However, its reconstruction procedure relies on the estimation of the path lengths where transient where measured transients are discontinuous. Thus, it can be sensitive to inaccurate discontinuity detection. Besides, the reconstruction quality may suffer if we do not have sufficient dense measurements for estimating format path length gradients through interpolation. What's more, compared to the format path approach with the back projection method, both of them could reproduce the same part of the in-loss thing. And further exploration of connections between these approaches may help shed light into their fundamental limits and strengths. And combining geometric and radiometric approaches for in-loss imaging or other related applications will be promising in the future. That's all for today's lecture. Thanks.